Welcome to our integration series. Today we have this interesting integral here. It's a definite integral of arcsin of x over x squared from 1 over 2 to 1. Alright, we'll use integration by parts here in the following way. We'll take u as arcsin of x and dv as 1 over x squared dx. We do so because we don't know the antiderivative of arcsin of x, but it's easier to compute its derivative, and the antiderivative of 1 over x squared is clear. From here, continuing integration by parts, we want to compute du. Let's do so. It will be the derivative of arcsin of x, which is 1 over square root of 1 minus x squared dx. Now the antiderivative of 1 over x squared, experienced users, they know that it's 1 over minus 1 over x, but if you have some troubles, it's easy to do because it's a known integral of an x to the power of n, and we can do this by expressing 1 over x squared as x to the minus 2, and writing it like its integral will be x to the minus 2 plus 1 over minus 2 plus 1. Right, which will be x to the minus 1 over minus 1, and it's the same as minus 1 over x. Okay, I just did this to know that if you are in a stressed situation, you can just use the known identities to compute some integrals. Okay, now that we have our integration by part substitutions, we can proceed with our integral. It was here, I'll put a star. Also, let me, for the sake of convenience, only mention that we want to have the form of u times v minus integral of v du, right? Yes. Okay, now computing, we'll have our integral is equal to arcsin of x times minus 1 over x, and we evaluate this from minus 1 over 2 to 1, minus an integral of v du, it's minus 1 over x again, times 1 over square root of 1 minus x squared dx. And it's also a definite integral from, well, it was 1 over 2 here, pardon me, we should write just 1 over 2, yeah, from 1 over 2 to 1. Great. Now let's clear it up a little. I want to evaluate this directly. What we have here, let's think a little. We have arcsin of 1 times, well, over 1 with minus times arcsin of 1 over 2 over 1 over 2. Right, this itself is equal to, we have arcsin of 1 here, it's pi over 2, right, with minus, then these two minuses, they turn into plus, we have plus, arcsin of 1 over 2, it was pi over 6, right, 30 degrees, pi over 6, and it's over 2, which is 2 times, like instead of this we can write 2 times arcsin of 1 over 2, and multiplying this by pi over 6 we get like pi over 3, right? So we have in the end minus pi over 2 plus pi over 3. Now I hope this part is clear. Nevertheless, if you have some questions, feel free to write them in the comment section below. Okay, for a definite integral of minus arcsin of x over x, we have minus pi over 2 plus pi over 3. Now we have also plus this integral, plus minus gives plus an integral from 1 over 2 to 1 of dx over x times 1 minus x squared square root. Deleting this part, we now need to compute this integral, and before diving into it, I want to make a little discussion on an integrals where the term square root of a square minus x square appears. Usually, when we have such a structure, we want to use a substitution of x is equal to a times sine of theta. It comes mainly from the fact that the derivative of arc sine of x is equal to 1 over 1 minus x squared. Turning back to our substitution, now this substitution is the same as, it's equivalent to theta is equal to arc sine of x over a, right? Because we have x over a is equal to sine of theta. Yeah. And a subtle part of this thing is to consider that a is bigger than 0 and that this expression, like the function, say a square minus x square, a domain of minus a to a, and it means like x is between a and minus a, which means that the theta is between minus pi over 2 and pi over 2, and for this interval we have that cosine of theta is bigger than or equal to 0. We will use it later on, namely here. Like after this substitution, we go back to the expression that we had, and we can write this as a square minus, instead of x we took a times sine of theta, we can write it as a square sine square of theta, which will equal to a square times 1 minus sine square of theta, right? And this expression is a square cosine square of theta, right? Because sine square theta plus cosine square theta is 1. It's a famous identity. From this point on, we have a times cosine of theta in an absolute value. Well, a is bigger than 0, we considered this. The simple thing, we can just write a times absolute value of cosine theta. And since we consider this interval, namely theta is between minus pi over 2 and pi over 2, where the cosine of theta is bigger than 0, we can equate this to a times cosine theta. So we get rid of the absolute value here, which is important to compute our integral. So usually you don't care that much about what I wrote, because we can just derive it one time and then use it over and over when you see such an integral. But I decided to mention this now because I didn't use it before in our video sequences. Perhaps later on I won't dive into these details that much. But for computational purposes, you can just use this substitution and later on writing this expression as a times cosine of theta, and it will be just fine. Now, going back to our problem, I have some little space here and I'll use it to write our substitution. We have x is equal to sine of theta, because instead of a we have 1, and then dx will be cosine of theta d theta, right? So putting this to our integral, we have, first let's compute this value. It's what? It's minus 3 pi plus 2 pi over 6. It's minus pi over 6, right? We have then minus pi over 6. Well, we are working here. We switch from this line to this one. We have minus pi over 6, which is the sum of these two, and an integral, definite integral of dx over x times square root of 1 minus x squared with the following substitution. Now let's write the integral itself. We have plus an integral of, first let's compute boundaries. since we have x is equal to sine of theta, our boundaries will change for theta. First one is x equal to 1, which is sine of theta is equal to 1, and theta is pi over 2. Also we have x equal to 1 over 2. In this case we have is equal to pi over 6, right? We have our boundaries in our hands, so it's from pi over 6 to pi over 2. Now instead of dx we have cosine of theta d theta. Well, cosine of theta d theta over x times square root of 1 minus x squared. X is sine of theta times, well, this expression 1 minus x squared, I showed it here, we can just make use of it. It will be cosine of theta itself, because it's just 1 minus square root of x, like square root of sine of theta. It will be square root of cosine of theta, and since cosine of theta is bigger than 0, it will just be cosine of theta. Hence I just write cosine of theta in the denominator near sine of theta, the cosine of theta. Great, because cosine of theta, they will cancel out each other and we'll be left with 1 over sine theta. Now we have minus pi over 6 plus an integral of d theta over sine of theta from pi over 6 to pi over 2. Now you can note that this thing here is actually just cosecant of theta, right? So we have minus pi over 6 plus definite integral from pi over 6 to pi over 2 of cosecant theta d theta. Now a quick reminder that an integral of cosecant of theta, well, let's write integral of cosecant of x dx is equal to minus ln of cosecant x plus cotangent of x. I'll probably make a video computing on like this integral of cosecant of x, but this is a standard integral. Perhaps like some of you should know this to not lose time in deriving this. Alright, so we can continue. We have minus pi over 6 plus, well, actually minus ln of cosecant theta plus cotangent of theta from pi over 6 to pi over 2, right? And all that remains is to put the boundaries and get a final answer. For this we again write minus pi over 6 minus, first we have ln of cosecant of pi over 2 plus cotangent of pi over 2 and minus ln of this thing, which will turn into a plus of ln of cosecant of pi over 2 plus cotangent of pi over, well, sorry, pi over 6, right? We are in the lower boundary, pi over 6. Okay, now our final answer is, it's minus ln of, let's quickly remember the cosecant of pi over 2. It's 1 over sine of pi over 2. Sine of pi over 2 is 1, so we have 1 for this. Then cotangent of pi over 2, it's cosine of pi over 2 over sine of pi over 2, where like this is 1, this is 0, so it's 0, which means that for this expression we have ln of 1 plus ln of cosecant of pi over 6 is 1 over sine of pi over 6. Sine of pi over 6, which is 1 over 2. 1 over 1 over 2, it's 2. So we have ln 2. Now cotangent of pi over 6 is cosine of pi over 6 over sine of pi over 6. Now let's remember this. Sine of pi over 6 was 1 over 2, right? And cosine of pi over 6 is square root of 3 over 2. Then 2, they cancel each out, so we are left with square root of 3. So we have ln of 2 plus square root of 3. Like I wrote 2 earlier, so it's plus square root of 3. Now, seems that we have our answer, and it's the final one. Let's see how we can simplify it further. We can just write these together, right? Because ln 1 is actually 0. It's e to the power of something, which gives 1. It's by definition. So we have just ln of, we don't even need an absolute value. This is positive. So it's 2 plus square root of 3 minus pi over 6. This is our final answer to the definite integral that we were looking for. Yeah, here it is. Please take a look of what we did. If you have any questions, feel free to write them in the comment section below. Again, we could skip this part. I just did it for one time. Later on I want to do this perhaps. Yeah. Then we computed boundaries and got a final answer. If you have any questions, feel free to write them in the comment section below, and bye.